So now we're moving into chapter 15, which is on equilibrium, and we're going to spend a few chapters talking about equilibrium. So picking up where we left off before with kinetics and rates. Initially, when you have a reaction happen, you lose some reactants and you form products. So if I have N2O4 here, dinitrogen tetroxide, it is this colorless chemical gas. And as it turns into nitrogen dioxide, it turns brown. And then at some point, that darkness of brown that happens will stay consistent. Now, does that mean we completely ran out of all of the N2O4? Not necessarily. So as we saw from kinetics, if we look down here, initially I'm going to lose some reactants. And in that chapter, we mostly just studied what's going on here and here, and how does this curve kind of end up looking, and what kind of relationship does it follow. But once it starts to even out, that's when we hit equilibrium, and that is when our forward reaction and our reverse reaction happen at the same rate. So they're both still happening, but the rate is constant and similar. So both the forward and reverse reactions are going to be happening. So as I lose some reactant, I form product. And now that I have product, some of that product will form reactant. But once we reach the equilibrium phase, then the amount that we have of our reactant and product will be constant. This is called dynamic equilibrium. We have heard about this before when we talked about vapor pressure and saturation and that kind of thing. But now we're going to be talking about, instead of phases, we'll talk about actual chemical reactions. So, like I said, products and reactants are both being made at the same rate. The total amount of reactant and product doesn't change, but there are literal molecules that are reacting just at the same amount. So it won't look like the total concentration will be the same at any given point. For this to happen, for us to reach equilibrium, then we cannot have any of our reactants or products leaving the system. They cannot escape, because then we are not maintaining that concentration, and then the concentration can't be constant. So if we look back at that reaction, if I have dinitrogen tetroxide gas, a colorless one, going to nitrogen dioxide, we use this double arrow here, half forward, half reverse, to show that we are in equilibrium at that point. So if I have my forward reaction written as this way with one arrow going forward, and then I can write the reverse reaction happening that way. So now my product is my reactant. So that's my reverse reaction. So once we hit equilibrium, our rates are equal. So our forward reaction is equal to the reverse reaction. And this should look very similar to when we did mechanisms. So if I did that for my forward reaction, I would write that the rate for this forward reaction equals the forward rate constant times by my reactant, so N2O4. If I was doing this like a mechanism. For my reverse reaction here, this rate is going to be equal to the reverse rate constant times by my reactants now, which are the N2O or NO2, and then that would be squared if it was a mechanism. So since they are equal to each other, we'll write them, we'll put those equations in. So my forward rate reaction is my forward rate constant times N2O4, right, coming from over here. And my reverse rate, that's going to equal K reverse times NO2 squared. So if I rewrite this and I have my relationship, I put solve for Kf over Kr. So I'm going to divide. I'll do it in a different color. I'm going to divide by Kr to get my rate constants by themselves, and divide by N2O4. So if I have my forward rate constant divided by my reverse rate constant, that gives me NO2 squared concentration divided by N2O4. And this is equal to a constant which we call KEQ, the equilibrium rate constant. And it will basically be my products over my reactants. So that is the basis for equilibrium and the equilibrium rate constant. Now we'll focus a lot on what that looks like.